water from a container, the water travels alongside the container instead of straight downward where you are trying to pour it? Today I will provide a fluid mechanics explanation of why this phenomenon occurs. In the following examples and calculations, only wetting liquids such as water will be considered. Common household liquids are all wetting liquids, meaning that as stated here in the book, the force of a liquid's adhesion to the molecules on the surface of its container is greater than the force of the cohesion between the liquid's molecules. Therefore, the water is likely to be attracted to the cup or container it is in even when being poured out. Another reason why the water tends to be attracted to the container has to do with pressure differences in the water exiting the container and the atmospheric pressure surrounding it. This can be proved as an application of Bernoulli's equation. Bernoulli's equation involves variables of density, height, pressure, and velocity. In this example, the liquid's reference will not change in the system and are considered incompressible, so the density remains constant. The height difference in the liquid being poured is negligible. Other assumptions include assuming the liquid is in a state of one-dimensional steady flow and neglecting friction and other losses. This is necessary so the continuity equation can be applied later. Here is the typical form of Bernoulli's equation. Since the height is neglected, the z on both sides cancels out. We assume the height difference to be relatively small from point 1 to point 2. Specific gravity and gravity are known, so now we have to find a relationship between the last two unknowns, pressure and velocity. This sketch shows the water distribution when pouring water at a small angle. This will help us apply the continuity equation, which says that velocity times area at one position must be equal to the velocity times area in the next position during steady flow. Since the area decreases as the liquid is poured, this means the velocity must also increase to satisfy continuity. Using this comparison, we can simplify Bernoulli's equation and solve for pressure difference. The result is that the pressure inside the container is more than the pressure outside the container. Therefore, the pressure of the liquid outside on the container is less than the atmospheric pressure, causing the atmosphere to force the liquid upward against the container. This is shown especially in the first diagram. As liquid falls over the edge of the cup, it continues to follow the same path directed by external atmospheric forces and internal adhesion forces. The other free body diagram shows the combination of forces which allows the water to continue traveling along the container instead of following the path of gravity. We know that water does not always fall along the side of the container it is being poured from, so what is the difference between water which follows the container and water which falls downward according to gravity? The deciding factor has to do with the angle at which the liquid is being poured, since the angle affects the area, which affects the velocity, which affects the pressure difference. Generally, if the force of gravity is greater than the force caused by atmospheric pressure difference and adhesion, the water will fall downward. In the following example, adhesive forces will be neglected so that we can make a generalization about the angle at which a liquid must be poured to follow the path of gravity. The first sketch shows the previous example in which the angle between the negative x-axis and the container edge is positive. The area decreases as it is poured. The sketch on the right shows that if the angle between the container edge and the negative x-axis is negative, the area becomes greater as it is poured. According to the continuity in Bernoulli's equations, this gives us the opposite conclusion as before. If the angle is 0, then there will be no pressure difference, and as the angle increases, the pressure will increase, allowing the force of gravity to overtake any adhesive or pressure forces. Since this is an idealization, these exact angle rules do not always apply. Factoring back in adhesion as shown in the sketch and factoring in adhesive properties of the liquid and container, gravity can overcome pressure and adhesive forces at different angles depending on the scenario. Now that we have reviewed the math behind the phenomenon, let's review the videos again. The first video shows water being poured at a positive angle, which causes the water to follow the path of the container. This video shows water in the same conditions in the same container being poured at an angle closer to 0, therefore with greater speed. The last video shows water in the same conditions and angle as the first video, but being poured from a differently shaped cup made from different materials. These videos show the variables that decide when water will follow a different path.